Hello, 2011 Form A, number 4. This is for both calculus A, B, and BC. Graphical analysis. So, what do we have? We have a function f. We know it's continuous on the closed interval. So those curvy shapes are actually 2 quarter circles and 1 line segment. And we have an equation for g of x. So part A, we want g of negative 3. Well, if we have g of x, all we have to do is replace x with negative 3. So g of negative 3 would be 2 times negative 3, and the integral from 0 to negative 3, whoops, daisies, so the integral, since we don't have a function, we can't use a fundamental theorem, but we know it's net area. And if you look at this problem, we're actually going backwards. So we're integrating starting at 0 and going to negative 3. So we should know that when you integrate backwards, it's the opposite of going forwards. So it's net area, except the area on top is negative. The area below is positive. So if you want to find the area of that shaded region, it's a quarter circle. Well, the area of a circle is pi r squared. The radius is 3. It's only a fourth of a circle, so it's over 4. There's our answer. We're done. You could simplify that. You would get negative 6 plus 9 pi over 4. Again, you shouldn't simplify it. Oh, Yoshida made a mistake. What did I just say? If you integrate backwards, it's opposite. Since this area is above, and we're going backward, it should be minus, not plus. That should be minus, not plus. All right, that's part of part A. But we should read the question. You might fail to answer the question completely if you don't. So we found g of negative 3. But now we're asked to find g prime of x. So the derivative of 2x quite easily is 2. And here is what we have to see. Our function's g and our variable's x. If you take the derivative of an integral from a constant to your variable, so that variable has to match that. Then we learn all we need to do is plug that in for t. So we get f of x. So that is g prime of x. Then we want g prime at negative 3. So replace all x's with negative 3. If you look, f at negative 3 is 0. So we have an answer of 2. All right, that's part A. Let's go to part B. So let me erase a few things here. So part B, determine the x-coordinates of the point at which g has an absolute maximum. So keyword, it's not a relative, it's absolute. So what should come to your head? Absolute maximums on a closed interval occur at critical points or endpoints. So we know the endpoints, clearly given. we need to find the critical points. Well, we should know that's when the derivative is equal to 0. Subtract 2 from both sides. So when f of x is -2, where does that happen? Let me show you. Let's do this in red. -2 is right there. Whoopsies. So that occurs right there. So what we need to look at is the slope of this line. If you look, there's your rise, there's your run, but that's kind of in between. How do we know that's exactly 1.5? So to be safe, we should take our rise all the way down to here. So that clearly goes from 3 down to -3. So that's going to be down 6. And this is 3. So the slope of this line will be -6/3 or -2. So let's take a look here. We probably, to be safe, should write the equation of this line. Okay, it goes through that point here, which is 0, 3, and the slope is -2, so it's going to be y minus y1 equals -2, x minus 0. So it's going to be 3 minus 2x. So we want to know the x value when y is -2. So if we do that, subtract 3 from both sides, divide both sides by -2. So that's the x-coordinate for our critical point. That happens at x equals 5/2. So now we found the critical point. Now we have to find the value of g at the critical points and the endpoints. So we need g at -4. That's one endpoint. G at 5/2, and then g at 3. Well, we didn't find any of these, did we? So we're going to actually have to find these values. Now, there's actually another way to do this. So this is one way, and we'll go ahead and do this, but there's actually a shorter way. So g of -4, I'm going to place -4 in here and here and here. Let me get rid of some of this stuff. Whoops. So -4 times 2. Let me get my mouse turned on here, guys, so you can see what I'm doing. So this -4 plugged here, -4 times 2 is -8. And I'm going to integrate from 0 to -4. So I'm going to actually go from here all the way to here. So that's going to be minus the area on top plus the area on the bottom. We have 2 quarter circles. So this one here we're going to add. So it's plus pi r squared over 4. And we're going to subtract this area. So it's going to be pi r squared over 4. So that's g of negative 4. Then let's do g of 3. If I plug a 3 here, I'm going to get 6. Integral from 0 to 3. So now I'm going to integrate from here to here. So what that's going to be is this area minus this area, but those triangles are exactly the same. So that's going to be 0. So we're done with that. This one, negative 8. And then pi over 4 minus 9 pi over 4. That's going to be minus 8 pi over 4, or minus 2 pi. And then if I plug in 2.5 here, 5 over 2, that will be 5. Get rid of that line. And then I want to integrate from 0 to 5 over 2. So let me get rid of that. So I'm going to go from 0 to 5 over 2. It's that. So the area on top, let's go ahead and look at this area here. It's 1/2. The base is 3/2. So 1/2 base times height, the height is 3. So that's going to be 9/4 minus, and we want to do okay, let's take a look here now. That one right there. So this area. It's 1/2 the base. The base is 1, and the height is 2, or negative. It's 2. The area is positive. So that's going to be 1. So that's going to be, excuse me, 5 minus 2.5 minus 1. So 5 minus, actually it's 2 1/4 minus 3 1/4 will be 1 3/4. Now we're looking for absolute maximum. Why is my brain on drugs here? Something isn't quite right, but let me take a look at what we've done so far. We want the maximum of G. So we put in our endpoints and critical points. So we put in 3, which gave us 6 minus 0, 5/2, which is 5. Oh, poopers, scoopers, I just realized what happened. This is plus this area above minus the area below. That changes all of this. Okay, so it's 5 plus 2 1/4 minus 1. So 5 is 6 1/4. Okay, now I feel better. So clearly the maximum value is 6 1/4, but they're asking the value of x. Nope, wrong one. The x coordinate. It's 5/2. So now you have a conclusion. Therefore, g of x has a maximum at x equals 5 over 2. And we're done with that. But let me show you another way to look at this, which is much, much faster and prettier and less work. So I will do it on this side over here. So we're still going to use the fact that we found a critical point. 5 halves. And we're going to do something here. Now, I don't want to confuse you because some of you might think, hey, I'm looking for a relative max or relative min. That's not how you find absolute maxes. They happen at critical points, endpoints. But there's another theorem going on here that's going to be muy importante. So I'm going to plug in an easy number like 2 and 3. Okay, here is G prime right here. So if I plug in f of 2 is 0. That's going to be clearly positive. If I plug in 3, f of 3 is negative 3. It's right there. So 2 minus 3 that's clearly negative here. So it shows that there's a relative max of 5 halves, but there's a theorem. If you guys remember this, this saves you a lot of time and a lot of effort on a lot of problems. Not a lot, on some of these problems. If you only have one critical point, that critical point must be an absolute max or an absolute min if it changes, your derivative changes signs. Because think about this logically. What does a positive derivative mean? So from our left endpoint to our critical point, in that whole region, your derivative is positive, so your function has to increase on that whole region. And then from 5 halves to 3, your derivative is negative, meaning your function must be decreasing. Clearly, that point must be a maximum. And if the derivative goes from negative to positive, there has to be a minimum, but that works when you have only a single critical point because it can't change directions anywhere else. So that's what we would do. So we would show that the derivative changes from positive to negative at 5 halves, and that is the only critical point. Therefore, that must be a maximum. I'm not going to write that out, but that's the other way to do that problem. This problem's going to take a while, isn't it? We still have 2 more parts to go. I'm sad for you guys because I'm going to have to erase all this here. I'm not sad for you guys. You probably miss hearing my beautiful voice, miss the fun of calculus, and you enjoy this extra time immensely. My nose is running. I don't know if I should blow it or just keep going. I'll just keep going. Okay. Keyword, point of inflection for G. So we should know that a point of inflection occurs when the second derivative changes signs. So we need to find the second derivative. Now, I erased the first derivative. It was here. So the second derivative of G is f prime of x. So that's what we need. So we need the second derivative to change signs, or the first derivative of f to change signs. So that's what we're going to look at. So we don't have the graph of G, but we have the graph of f. And so we should know from the graph of f, if f is increasing, which it is on this region, then f prime is positive. And if f is decreasing, which it is on that side, f prime is negative. But f prime is g double prime. So if you look at that, f prime changes signs, or g double prime changes signs right at the apex there. That means that's where my inflection point is. But that's my final statement. There's an inflection point at x equals 0 because the second derivative changes signs. But how do I get there? I have to show that the second derivative changes signs. So what I'm going to do is say, since f is increasing on the interval from -4 to 0, therefore f prime, which is g double prime, is positive. Beautiful. Then we're going to do the same thing to the right. We're going to show from 0 to 3, since f is decreasing, f prime, or g double prime, is negative. So, since f is decreasing on the interval from 0 to 3, therefore, f prime, which is g double prime, is negative. I should have said on that interval. On that interval. Okay, so we see there is a point where g double prime changes signs, and namely at 0. Because up to 0, it's positive g double prime, and after 0, g double prime is negative. So we are finished. Therefore, g has an inflection, point at x equals 0 because g double prime changes signs at x equals 0. Dunno. That wasn't too bad. And then part D, let me erase all this by putting a white box over all that work. All right. I don't know if I can erase this stuff below it. There we go. Okay. The average rate of change on the interval, we have to find that. So part D, that's pretty easy. Average rate of change is f of b minus f of a over b minus a. So f of 3 we see is -3, and f of -4 is -1, so it's -3 minus -1 over 7. So it's going to be -2/7. So that's the average rate of change. So you may want to label this better. So the average rate of change is that. Now, what's it asking? The mean value theorem says that there must be a point where the average rate of change equals the instantaneous rate of change, or the derivative, where the derivative equals the average. And it has to occur somewhere in that interval. So why is this not true? It's supposed to be true according to the mean value theorem. So we know the mean value theorem works. So it must have to do with the conditions. You need to know the conditions for the mean value theorem. The first condition for the mean value theorem is it must be continuous on a closed interval. And the second must be true. It must be differentiable on the open interval. So those must be true for the mean value theorem to apply. Well, we know it's continuous because that was given to us right there. Bam, continuous on the closed interval. So we're good on that. But nowhere are we given differentiability. And if you look on F, it clearly is not differentiable at 0. So explain why this statement does not contradict the mean value theorem. Okay, this you wouldn't write down. Whoa, that's kind of weird. Weird. That's really weird. Okay. So it doesn't meet the conditions. So you would say, since F is not differentiable at x equals 0, therefore the mean value theorem does not apply. Bam. Now, I just looked at the solutions. They also noted another point where it's not differentiable. I'll point that out for you. So right here, it's a vertical asymptote. So the derivative does not exist at -3. Now, you don't need to state that because once you show that the derivative doesn't exist at one point, done, mean value theorem does not have to apply, or does not apply actually. So you don't have to show that there's actually a second point here where the derivative does not exist. You could have used either one of those, or you could show both. I think that was a long video, but hopefully you guys learned something. I guess that's it. Bye.